All right. Good morning, everybody. Can you hear me? Are we good? Yes, thumbs up. All right, rocking and rolling. Okay, so thank you all so much for being here. CSAT 2021 hybrid. This is our first ever hybrid event. It's pretty awesome. So huge shout out, first of all, to all of you for being here. To the staff at the Doubletree and the CSAT who have pulled all this together. We've never done it before, right? So there's going to be some hiccups along the way. But just before we get started, just a round of applause for all the hard work that went into making this happen to start with. All right, beautiful. So you don't want to hear me for too much longer, but I'm the logistics guy for this morning. So a few things to be aware of, right? There's about 100 of us here. There's somewhere between 400 and 700 online. We'll figure out where that exact number lands, but thanks to everybody who's online from around the world. Apologies to those who it's 4 in the morning or 5 in the morning or 3 in the morning. We have presentations coming from around the world, right? So we have folks from Australia, the UK, Canada. We've got folks who are here in Leominster, Massachusetts. We've got folks who are across the country. So this is truly an international presence. We're excited to have everybody and be part of this. All right, because it's that hybrid mentality though, because people are all around the world, all around the country, bear with us through any technical difficulties, right? When you have questions, shout them out to speakers. Speakers, repeat them back. The microphone's hooked up so that everybody virtually can hear us as well as everybody in the room, right? So speakers, make sure you're repeating all of those questions. We'll keep things pretty on pace here. We've got to make sure that we're prompt and on time because otherwise schedules are going to fall apart. And if schedules are falling apart, then the people who are at home or in the office and not here with us are not going to know where we are. So we're going to try and keep things short and sweet. You can always look down to this table right here. We'll give you a 1-minute countdown just so you know kind of where your time slot is, and we'll try to keep things moving. For speakers, right, there's a nice screen right up here for you to see. There's also a clicker for you to use, okay? So that'll advance your slides forward and backwards. We will go through and have a couple of breaks. We'll have lunch, all of that kind of fun stuff. All of the food is just out to your right, my left. So whenever we do break for lunch or breaks, just make sure you're walking through these side doors and we'll queue up along these. So we'll queue up into the ballroom. Restrooms, if you haven't found them, are out to your back left, my right. So feel free to pop out there at any time. We are asking that we keep masks on unless you're actively consuming food. The reason for that is just, again, there's a lot of folks who are coming from around the world, around the country. We want to make sure everybody is safe and healthy both here and when they're going back home. All right, so bear with us. We'll figure this out as we go. If there are any questions, don't hesitate to reach out to anybody at the back table in the front entrance or myself or our wonderful host, Dr. Victor Champagne. So with that, I will turn it over to Vic and we can get this party kicked off. Thank you all very much.
Good morning, and it's so great to be here. It's so great to be in the midst of people, to be out and about, to see colleagues, friends that I haven't seen for a long time. Of course, it's tough. You see this mask, all you see is 2 eyes, and I got to figure out. I've been doing pretty good, though. It's not easy. So I've got a lot to say. I was just making a comment to Tom Stamey from Puget Sound Naval Shipyard on, I think we're going on our 12th year of CSAT, which is amazing. And every year we've grown considerably. I think the first year, I think we're just shy of like 100 people. And last year we were just shy of 800 people. So it's amazing. And every year I think, geez, what am I going to talk about next year? We've made such advancements in this area and that area. And this year, it's just amazing at the amount of progress, the accelerated transition and implementation, the number of systems, okay? I've contacted a number of the major equipment suppliers for cold spray, the center lines, the VRC, SPE 3D, Impact. Years ago, when I first started, geez, in the late 90s, and Keith Kowalski knows, I mean, he was one of the pioneers way back when, working with Dr. Anatoly on the first systems. with a K-Tech system, remember? I bought the first commercial system. There was a system at Sandia Labs as well, and we could count the number of systems on our hands. I talked to Julio, and he told me there's 150 center lines out there, right? And talked to Impact and CGT. Between the two, there's 120. VRC, there's 40. Speed 3D is about half of that in about half the amount of time. So I've got a lot to say. So with that, I welcome everybody. And we all know what CSAT is, right? It is not a formal, stuffed shirt conference. We're here to discuss, to debate, to go over, high points, low points, and to push forward the technology throughout the world. I want to make CSAT more international, and you'll see on the agenda, we're making an effort to do that. So if I can figure this out next. Okay. All right, State of the Union address, right? So I pulled this picture. It's Woodrow Wilson's State of the Union address in 1915. And prior to then, there were only two State of the Union addresses by George Washington and John Adams. Everybody else just basically put it in written form, which is interesting because, we have State of the Union addresses now. And so there are topic areas that I want to hit upon. I actually removed one. Manufacturing at the point of need, that's our theme. 3D printing, that is the future, big time. We advanced from non-structural repairs to structural repairs to doing some AM parts, but 3D printing is going to be the future, as well as structural repair. And that's where we're most definitely headed. You'll hear talks today from VRC, introducing their upcoming software about this time next year probably. They'll get into it. You'll hear talks from Speed 3D, which is already there. You'll hear about their collaborations. It's pretty fascinating. And manufacturing at the point of need, what does that mean? It's just what it says. So if I'm out in the middle of Afghanistan, out in the desert, and I need to be able to repair or make parts, I need to be able to do so. So that's manufacturing at the point of need. Cold spray feedstock powders. I'm gonna be telling a couple of stories about the importance of powders. There's no doubt about it that one of the attributes of cold spray is what? Being able to take commercially available, off-the-shelf thermal spray powders. You can do that. But you're gonna get to a point when you want to entertain structural repair, you want to entertain additive manufactured 3D printed parts without a lot of post-processing, garbage in, garbage out, the old computer adage. So I'm going to spend some time this morning. Helium recovery. Yeah, that's interesting, right? So we know a couple of things. We know in Europe, helium is, a no-no, right? It's hard to get. It's very expensive. Not that it's cheap here, but at least we can get it. It's from natural gas reserves, and we just tapped into the, as kids, we were told that we're going to run out of oil and gas, all right? Well, we've tapped into the largest reserves known to man, okay? Well, helium is a byproduct, so we're able to capture it in the United States, but it's still, you can view it as a finite commodity. It is expensive, 100 times more expensive than using nitrogen, but it's got big attributes, right? You get the highest velocities from using helium. So there's big efforts in trying to come up with helium-like properties using air and nitrogen, but there's helium recovery too, and I've got a few slides on that. So, to jump right in. The cold spray ecosystem. Creating that over 22 years. And I would say 90% of the people are tapped into that cold spray ecosystem that are sitting here today, either directly or indirectly. What is he talking about, ecosystem? Ecosystem consists of numerous universities, national laboratories, industry players, Department of Defense, energy, other research laboratories, I still refer to it as United Technologies Research Center, so it's Raytheon Technology Center. But lots of projects, programs that 1 year, that ecosystem sustained in upwards of $120 million, okay? And part of what you're here to do is to be networking, forming partnerships, future collaborations, taking what I say and a lot of these great speakers you're going to hear today and say, geez, wow, I didn't know you could do that, or look at what they're doing here, we should be doing that. And then finding out the people to work with to make that happen. I'm not going to go into these areas. You can read just as well as I can. But there's basic research opportunities, there's testing and qualification, there's certification, there's transition, there's implementation, there's the development and sales of feedstock powders, of equipment, of additional hardware, software, accessories, support equipment, etc. That's the ecosystem, and it is not a closed system, it's an open system. We try to make it be as much open as we can. We know cold spray. I've developed personally with my team through the years applications and transition into all these areas. Oil and gas, automotive, especially aerospace, right? I mean, that's basically the first industry that I targeted. But there's others, including medical, antimicrobial coatings you hear. And it's so funny, because the work that I did with the team, 2008 to 2010, published some papers, in like 12, 13, basically touting the benefits of antimicrobial coatings. Well, people are crawling out of the woodwork now. If they would have implemented stuff that I had said 10 years ago, we would have been much better off. So there's a lot of visionary statements that I make through the years, that other people make, presentations that you will hear today, and 5, 10 years from now, you'll be saying, geez, I heard that first at CSAT. And so with that, I'm going to throw up this slide. So part of what I've been doing is to substantiate some investments with folks that I work with, market studies. This just happened. You could pull this off the internet, all right? That's where I pulled it off. But it shows the tremendous upward trend. And a lot of these areas, I'm looking at Aaron Nardi through the years that we've developed, all right? We've developed and impacted a lot of these areas. So you see the significant rise. Now, I think in dollars, we're still about just shy of $2 billion, where thermal spray, I think Keith is are upwards of like $8 billion. And I firmly believe that we should be in upwards of that number. And with the advent of 3D printing, I think we should be surpassing that. I think that's what the future holds. I pulled this to show the importance of additive manufacturing. I'm going to tie it into manufacturing at the point of need and 3D printing. But this is a DoD mandate. And again, you can pull this off the internet. That's where I got it. You see the distribution statement. You see the website where I pulled it from. And this is a directive coming from DoD on the benefits, the attributes, and the go-forward plan. We need more lethal systems, powered by innovation designs, kind of a general statement. Increases material readiness, empowers warfighters to solve problems in the theater, right? We don't have to rely on a depot, we don't have to rely on a repair station in theater. But depends on, hey, how far advanced are we? Are we mature enough? Level of expertise, training, certification. You can buy a system, doesn't mean you know how to use it, all right? And then finally, data. Data, data, data. When I first started, the ESTCP program, which serves as the poster child for qualification of non-structural repair, is the one document right now that contains the most data on any one single material substrate combination. That's how I'll say it. And that's all going to contribute to how far we get. All right, I'm going to show you a couple of 2-3 examples. Highlights, again, over the last year or two. I wish Fred Lancaster were here, because, I mean, this is where he could bathe in the limelight. So this is a news press release on the VRC system, mobile system, repairing a windowsill area on the V22. So it's basically, it's a mobile system. You see it's attached to a robot. It can be manipulated out in the theater, out on a tarmac, wherever you need. And here's a quote from Fred. The future is with structural repair. And I'm going to go so far to say he's absolutely right and go beyond that. Structural repair and 3D printing. I'm going to give you another example of a different system. This is amazing too, and I just heard that this August, the Aussies and the U.S. Marines are going to be doing joint maneuvers out in Australia, out in the outback, and they're going to be taking a number of these systems out there, and not only producing parts, because they've done this, I think 2 or 3, I think this will be the 3rd time together. And actually, I heard about it, I'm looking at Aaron, because we had to do a tour for a general who basically said, hey, could you do this? I just came back and we maneuvers with the Australians and they're doing this. And so you see, basically, the SP3D unit, instead of that bright fire engine red, is camouflage, right? Because that wouldn't go over well in the theater. You'd be a target. But they're making parts. And not only that, they are going to be inserting and testing those parts in theater over, I think, a 2-week period. So that's pretty neat. All right, these 2 good-looking guys, right? This is over the last year. All right, and here's my quote. All right, and I've said this since day one. It's not just a coating technology. It's not just for repair. The future is going to be, and so in 3D printing. So that was printed like last August, July. This thing has a delay. Here's a near-net shaped part. It was produced a couple years ago, 2018, introduced into the Patriot missile. The future of cold spray systems. I just want to, and I'm going to end with this too. When we, at the end notes on the second day, I'm going to end and go into this in more detail. But what I see in the future perfect system, and I had said this when I was the keynote speaker at the 2007 International Cold Spray Conference, the 2011, and I'm going to say it today in a different note. The future system, it's got to be flexible. What does he mean by that? And it's got to be adaptable. Flexible, adaptable. I want that future system to be able to do high pressure, to be able to do low pressure, to be able to have software and hardware to do 3D printing. I want that system to be modular in concept, but at the same time be turnkey. I want that system to be able to fit in the manhole cover in a submarine because of its modular concept, being able to be taken apart and put back together again. Or I want it in a production setting or out in the middle of the desert or anywhere else. I want it to be repeatable. That's not just me, all right? Whole additive manufacturing industry, it's got to be repeatable. You've got to get repeatable results. They got to be reliable results too, all right? Am I hitting the requirements, the specifications? Got to be robust, all right? I don't want to take some laboratory system out in the middle of a desert and it falling apart because some dust infiltrated it or I take it out in Alaska and, a pump freezes up because, it's not made to withstand cold weather. And I want it turnkey. And I don't want to be saying, you got to buy this, you got to buy that. Well, we don't do this. No, turnkey. Okay? Tell you a little story. Not all powders are created equal. All right? And I've got a lot to say, and I got to blow through these slides, but it's important. And I don't want people using that argument against me by saying, oh, look, you got to buy special powders in order to use this system or that system. Oh, I don't want that. I want to be able to use off the shelf. And that's fine. Number one, you can buy these powders off the shelf that are made specific, all right? But number two, if you're doing a bubble gum repair, and I call the bubble gum repairs what? You're using BHOD, you're using epoxy repair. You got a ding in something, you put a little epoxy. I don't care what kind of powder you use, and it doesn't really matter a whole hell of a lot. But when you go to structural repair, when you go to making a 3D printed part and you don't want to post-process, heat treat, anneal, you don't put any work into your feedstock powders, garbage in, garbage out. Actually, I stole my own thunder, right? This thing has a delay. It's ticking me off. You have to actually press it a couple of times for it to do once. But anyway. This is aluminum powder, okay? So to the uneducated, I'm buying some aluminum powder, just give me the number and I'll call. You could get any one of these for aluminum powder. They all meet the chemistry. They'll all meet the past requirements for aluminum powder. I wouldn't meet it now because we've got flowability, we worked into the specification and other things, so you couldn't get all four of these. But a lot of people, they don't know the difference. This, 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 and this. Totally different. You don't want all ping pong balls. You don't want cornflakes. Think about how they tumble in the gas stream, and when they impact, the deposit is going to look like Swiss cheese. Agglomerate, pieces of coil stuck together. Deposit efficiency is going to go down the crapper on that, using that powder. This isn't bad. You got some block, but I see some acicular in there. I see some big old boys. You want aggregates. And that's just geometry. Did a little experiment. So a guy did his PhD thesis on this that I know. And what he did is he took as-received powder, he exposed it to humidity. And what I mean... Oh, they can't hear me online? Okay. All right. So you got to have one of these walking things. I got a little animated here. You got to chain me to this damn thing. So I can't see the slide. Actually, I wonder if this helps. No, that's worse. So anyway, we wanted to expose it to humidity. All right, and I fought with people. All right, from I won't say from where. From DOD, who told me that aluminum powder doesn't further oxidize, doesn't form when you get it in a gas atomized condition, it's not going to grow any more oxide. That's a bunch of crap, all right? And as a matter of fact, I got in a further slide, you know what they use aluminum powder for? Is a desiccant. What's a desiccant? Something you use to absorb water. Hello? How does it absorb water? It's a chemical reaction that takes place. All right, and you form hydroxides. Well, picture yourself at Corpus Christi Army Depot in the summer. Got a bucket of powder that you buy. Because you don't buy, typically they don't buy powder just for one spray trial or one spray run. No, they'll buy a bucket. They'll open that bucket up, put in what they need, and then leave the bucket open. And if you're lucky, they may close it. Doesn't matter. The experiment, we opened up the bucket, closed it, opened it up to simulate, like a couple, 2-3 weeks of doing that. And then we characterized those exposed powders, and we compared it to a baseline. Then we did single particle impact studies to see how it would impact the critical velocity required to have the particles stick and consolidate. All right, and then we made blocks of material, And we did all sorts of mechanical tests on it. We even did conductivity, did hardness, did UTS. And guess what? I've already said this. Yeah, I'm going to point this out again. For those that don't know, aluminum powder is a desiccant. And so for people that say, well, what test did you run? You know, you can read just as well as I did. I mean, we did everything under the sun to characterize the oxides, the hydroxides before and after. The most in-depth study that I've ever done, I bet you that anybody's ever done, that I've ever read by far. Look what happened to hydrogen. Look what happened to oxygen. Comparing it to the as received, to the group that was exposed to 95% humidity. It went through the roof. You don't get hydrogen from the formation of an oxide. You get it from the formation of the hydroxide. So it hydrolyzed. That powder hydrolyzed. I'm not going to point out all these different samples. We did experiments in heat treating the powders, and you see the differences in ductility. But the point I'm trying to make, you open a bucket of powder, it gets exposed to humidity, it's going in a crapper pretty quick. And we've experienced that firsthand before we knew this, all right? We got properties in the as-received powder that were great. We sprayed it a week later, and it was garbage. You're doing bubblegum repairs, doesn't matter. You're going to structural, you're going to 3D printed parts, you don't have specialized feedstock powders, you're asking for trouble. Differences in fractography, you know, I don't want to be just a talking head about programmatic stuff. I love the technical stuff. Ductile dimpled, all right, in the as received, intergranular brittle fracture, and the high humidity. So what did that mean? You got a oxide, hydroxide formed on the outside of that particle, all bombarded, formed a big block of material, bunch of oxide in there. You pull it, it's got no ductility whatsoever, and it fractures in a brittle fashion. You want that on an aircraft? I sure as hell don't. This is a process that we use now. We process the powder, we have preferred geometry, and I'm not going to go into all of the different QA tests that we do, but it's flowability, it's chemistry, it's geometry, it's particle size distribution, and it's packed inert. This is a fascinating study, and this was part of the PhD thesis. I had data which extended to a year at the time. Now we have data that extends out since 2017. I just did some averages and made that chart. But basically after 4 years, so think of a can of tuna. Whether you eat it on day one or you eat it 3 or 4 years from now, you're not going to get botulism and die. The cool thing about this is 4 years later, in that inert package, I can use the powder. So if I'm on an aircraft carrier out in the middle of the damn Pacific and it's humid as hell, that powder's protected and it's little cushy world in that inner environment saying, I don't feel the sea mist, I'm not hydrolyzing, I'm having a great time, I'm nice and dry. And if you get so inventive, which we have, you can develop a little nipple on this thing such that you've had a female and a male connector to your powder feeder. So even when you put it in a powder feeder, you don't even have to expose it for those few seconds or minutes, if your heart so desires, if you want to keep it to that level of control. And this is what happens. This is a single splat, a single particle. And I got 5. So these brightened areas and this dark area here, I'm going away from the mic again, represent areas that are unbonded, and that's where the hydroxides and the oxides are. I made a little cartoon All right, so don't think your Al powder has a nice little candy coating like an M&M of an aluminum oxide on it when it gets hydrolyzed, when you open it up at CCAD. No, it will hydrolyze immediately. Helium recovery I want to end with. Don't think that you can't use helium. You can. There's an actual system. Actually, I want to go back. That was the concept of just having a turnkey helium recovery system that would be efficient within a short period of time. That short period of time, it differs depending on how much flow you have. I don't have time to explain the entire system. You can see me afterwards. We can discuss it afterwards. But it becomes efficient, I'll say between 20, 30, maybe 40 minutes, depending on the flow rate. So if you've got a 5-minute spray, a 10-minute spray, you're not using this system. But anything else, you do use that system. It's recovering anywhere between, 94, 95% when it's fully in operation and you've got long sprays. That's kind of what it looks like. This is a little cartoon that I threw up, it's God's honest truth. When I was at ARL, and we were spending 800 grand a year, I mean, that's how many trailers we would have. With the helium recovery, if you were to use it, you'd see that those, 26 jumbo trailers would be reduced to like 1.5. This is my final slide. And yeah, I am proud of this. And we busted our hump putting this together. And I think it took us, I'm embarrassed to say, I think it was close to 4 years to put this thing together. You can buy it now. I think it came out this week. This is the first book, all right, that shows you from a practical perspective what cold spray is all about. You see the different chapters from setting up a system. This book has the most material properties. Oh, that's his book. He said, I don't get a dime for selling 1 or 1 billion copies. I work for Uncle Sam. I don't make a dime. I wish I did, because this is going to be a good book. Well, it is a good book. And you see the editors. I want to give credit to the editors. Ozon from Northeastern, Aaron Burt, Aaron Nardi. I'm looking at you, Aaron, because he's giving me, hey, you gotta finish, right? And so Aaron Nardi, I will say from ARL, he's with VRC now, but I was at ARL like 99% of the time when this was completed. But, it talks from a practical perspective. So a guy in a depot, this would be beneficial to. But then also an academic, it would be beneficial. Because it's got the theoretical explanation, but it's got the backbone of it is practicality. It's almost like a how-to book. You go to Home Depot, you want to put in your own sink, right? Your wife's on your case to put in your own sink. You don't want to hire a plumber, so you go out, and that's what this is. From setting up a system to qualifying a process to transition to implementation to specifications and standards and developing your own processes to feedstock powders to material properties and what tests should you be conducting, what inspection criteria should I be using, the whole 9 yards. So I'm going to end with that and introduce the next speaker, who's my bro, who left me. I'm crying still. But it's Aaron Nardi. He's with VRC Metal Systems, and he's going to be giving you a talk this morning. It's always good to hear him speak. It's such a wealth of information. He's been in it for many years, from a user perspective, from a hands-on perspective. So without any further ado, Aaron, I'll take the hook and I'll let you present.
Oh, just click forward? All right. Perfect. Hey, well, welcome everybody. It's great to actually see you guys in person again, and hopefully we'll see more folks, the folks online, next time that we do this. I'm going to talk to you today, as Vic mentioned, about manufacturing at the point of need using cold spray. I got a few different topics I'm going to cover in this talk. There we go. And that includes materials and process developments. It also includes some hardware developments, and then I'll focus on the types of equipment that we're working on for point of need manufacturing. So first, let's start off with some mechanical properties. I always like to get into something to do with powders and properties. So the goal of this project, this is done with NavAir FRC East. The goal of this project was to look at E357 cast material and see if we could repair typical blends that you would see in hardware. Now, when I say repairing a blend, generally parts, if you have a little bit of corrosion, you're allowed to do a certain amount of blending, a certain blend ratio, and that still meets the requirements of structural properties. So what we're looking at here is, can we repair that divot that was allowable and either give it additional strength or at a minimum, no debit in strength? So what you see here is some properties of 7050, and then F357 as repair materials for the E357 casting. And what's interesting about this is you'll see the strength values of each of these materials is actually higher than the E357 substrate. So in this particular case, we're spraying on material with a higher strength than the substrate material. So now let's see how it performs from a structural standpoint. There we go. So here you see an SN curve for the coupons, and you can see what the coupons look like too. So it's a kind of a divot in the middle of the coupon. So our baseline again is the divoted coupon. And the goal is to achieve more cycles to failure, right? Increased cycles to failure. So what we see here is you can see here is the baseline sample, and then when we do our repair, we're actually pushing the cycles out to here. The scatter band there is actually for D357. It's not E357, but this is the only data we had available to us. So that's what I'm plotting. So you can see we got an order of magnitude shift in the performance by doing this repair. So in fact, we are seeing structural load carrying capability out of the material. Now I have these drawn as lines, the yellow and the blue and so forth, because if you actually consider that we're carrying load, then the stress level is really only 21 KSI as opposed to 25 KSI. So we're not quite at the scatter band if you consider it as 21 KSI, but the fact is we're failing from defects in the substrate, not from the coating. And that's what's important here. The substrate is the limiting factor, not the cold spray material anymore. So we have a full structural capability out of these coupons. So now let's look at a different scenario. If we take that same 7050 material that we just talked about, the cold sprayed material, but now we apply it to a 7050 substrate instead. You can see that the wrought 7050 material has a higher strength capability than the cold sprayed material and a higher ductility. So now can we still use this for some sort of structural credit? Well, we find out we can. In fact, the baseline materials here are this green dot and this little red dot up here. And if you look at the improvement we get at both R equal 0.1 and R equal -1, we're seeing an increase in load carrying capacity. Now, we haven't gotten back to the full strength of the material. That would be where these blue arrows are. We would want to push those cycles out to that yellow line or that blue line. But we are getting increased capability over the divoted sample. So if you can allow a blend, then you can repair it with this and not have any further damage to the part. All right, so with that, I'm going to switch gears a little bit, and this gets into, as we start to transition to point of need use, can we go from having to generate nitrogen and use nitrogen, can we go to air? So we're looking at that for a couple different materials here. One is the WIP material that Vic talked about earlier, which is a nickel-based blend material. And then the other one is a aluminum blend using 7075 powder. So what you see is in both cases, if we look at posi test adhesion testing, so that's your normal glue failure button, right? And then you look at porosity, you see really no difference between these two. Now our predictions say that we should see something like a 2.5 to 3% reduction in the critical velocity ratio going to air. So where does that show up? Well, so far the only place it's showing up is in hardness. And while I guess it's debatable because the differences you're seeing are all within the typical scatter of a Vickers hardness test, you can see consistency from nitrogen to air where you are getting a little bit of a drop each time when we go from nitrogen to air. So we are seeing a slight difference. However, that amount of difference can be easily made up with process conditions. Modify process conditions and you're back to where you were with nitrogen. Okay, so that's my materials part of it. I'm going to talk about equipment now, a couple of equipment developments. One is in nozzles. This was a project looking at applying coatings to large surfaces. So if you want to apply a corrosion inhibiting coating, like a galvanic protection, for instance, to a large surface, how might you do that? Well, we know that cold spray has a very constrained plume, which is nice for us when we're trying to repair parts. It makes masking a lot easier and so forth. However, when you want to coat a large area, having a very constrained plume means you have to have very high accuracy of your path planning and so forth. So if we go to a wide area nozzle where we can spread that plume out a little bit, that'll make coating large surfaces easier. So we're looking at a couple different geometries. The first is, well, they're both an oval or an ellipse exit, but using a standard circular throat. And what we did was we took our nozzle 60, which is here, and we took the expansion ratio we had on nozzle 60, which works very well for a lot of these nitrogen sprays, and we opened up the exit to an ellipse, but maintaining the same aspect ratio, all right? And we got two different ellipse shapes here. So let's look at the performance. All right, when we, one of the first things we would look at is velocity, right? So if we look at the velocity of the particles, we have here a range for nozzle 60 and a much tighter range for 85 and 86, which are these two elliptical nozzles. The range of velocities that you see on the 60 is kind of interesting because the 787 meters per second is actually for a very lightly loaded stream, and if you load the stream up heavy, it drops down to 747. The nozzle 85 and 86, it didn't matter whether we loaded it heavy or light, we got the same result. We got 745 to 48, you know, all within a margin of error here. So now, if we want to look at what the deposition looks like, you can see these are plates that were made with 4 spots and a circle in the middle just to look at the different paths and what the mounds in the corners look like. And you can see that with the circular nozzle, as you'd expect, you get a little Hershey kiss, right? And then when you go to these elongated nozzles, you get this wide spread of material going all the way from 8.6 millimeter spread on the circular up to 15 on the widest spread. So now that's going to allow you to change your overlap, your step. So let's take a look at that. If we look at 4 or 5 different step conditions, 1 millimeter step all the way up to a 12 millimeter step, where 1 millimeter is kind of common for a lot of normal nozzles, normal spray processes. We see that we can go all the way up to 4 millimeters, and at this 4 millimeter step condition, we still have a very smooth surface. We have a nice, smooth, uniform surface, and that's because the distribution of particles that we have is still Gaussian. So now you can overlap those, and you can kind of fine-tune that and get a nice, smooth surface. As we go all the way up to 12, we do have some undulation in the surface, some waviness. However, we still have complete coverage. So if what you're looking to do is just cover a surface with a galvanic protective material, you can still do that all the way up to 12 millimeters. All right. Next piece of equipment would be the Dragonfly. Now, we talked about this in previous years. I know the Navy's talked about this as well. This was a Navy program in order to fit a cold spray system down the hatch of a submarine. Well, we've modified the design, and we've turned it into a commercial product now, and with that came a couple interesting advances. One is that the hardware was changed inside the cabinet to actually increase the ability to change recipes on the fly. So now you can go from one recipe to another without opening the thing up and changing orifices and things like that, right? And we also added this pendant, which is a little more advanced, and I'll kind of show you a little bit about that. So here's the functionality of the pendant itself. Oh, by the way, the system still has the same performance characteristics of 1,000 psi, 800 C as the regular systems. But in this case, one of the unique parts about this pendant is it's preloaded with recipes. So in this case, you don't get, like Vic was saying, you get a cold spray system, now you can't run it, right? You need to learn how to run it. Well, in this case, it's preloaded with certain recipes so that once you get it, you can immediately go in, select those recipes. They're pre-qualified. We give you data sheets with them so that you know what you're supposed to get at the end. And then you can start going, and the operation is very simple. It's a 4-button operation. Once you select your recipe, you press, one of 4 buttons to start the system, stop it, turn the powder feed on and off, and that's it. So this is very turnkey, getting back to your point, very turnkey for people in the field. All right, so now we've talked about materials, we've talked about some equipment. Let's talk about how do we put this out at the point of need for the warfighter or for other commercial entities to use. And here we have a trailer system. So this is very similar to what Fred Lancaster had shown in previous years and what Vic had talked about today with the repair of that V-22. The major difference with this trailer system is it's got onboard gas generation. So in this case, we have air compression and gas cylinders so that this thing can operate all day long and then operate again the next day, and you don't have to keep bringing in tanks and so forth. It's also got another, I guess, portable platform for the robot, which I'll show you on the next slide. There we go. So this portable platform for the robot is it's a electric cart, basically. It looks kind of like a beach cart to me, but so you've got this cart with a robot arm on the top of it, which also houses your heater and your powder feeder. So you can wheel this over to the aircraft or the vehicle you're working on, and then put down these little outriggers to stabilize the unit, and then you can run the robot and repair your part or your vehicle. If you're doing a hand spray, it also, you can dismount the gun from the robot, and then you could do your hand spray, but you still have all of your equipment right next to you, which is a little bit convenient. And so the last one I'm going to leave you with is what we're calling the mobile parts hospital. Now, this trailer and the mobile parts hospital were both envisioned through this OSD Mantech program. This one is unique. It's not something that we've ever done before. And what's interesting about it is it's a complete turnkey system that you drop in place wherever in the field you want it to be. And this is a full manufacturing cell for cold spray operations. So this has your, this is going to have your power generation, gases, and I'll show you that in a little video clip here. And this one's due to be completed in August of this year. The trailer is due in October of this year. So I think this should, hey, it worked. All right, so what you're going to see here is just a visualization of the unit. And it's got doors, not just on the ends, but it's got doors on the side so you can access each of the components as you go. Here's where the compressors are. So that's a compressor and tanks. This is enough gas to run for continuously 8 hours of operation at the max flow for the systems. If you're running at less than max flow, it will actually run for even longer. You can run it almost indefinitely at roughly, I think 800 liters a minute. If you're running around there, you can run indefinitely. In the next compartment over, you have this generator, and this is a 125 kilowatt generator. So this supplies the power for the cold spray system, the robot, the heaters, the air conditioners, all the stuff inside this unit. It's all climate controlled and so forth. And then in the next compartment, so this is kind of what we call the utility box. So it's got the generator and the compressor in it. It's got a little area at the end of it, which right over here, which should open up, and that will show you a work area. So where these two join up, there's a joint right here that joins this this work area to the next work area. So your actual spray operations would happen in this area. Your dust collector sits here. Your control systems sit here. And then the final location, this door, when that opens, will be your actual spray booth. So this is a full spray booth with a welding table, dust collector, robotic arm. You can do all your work, whether it be additive manufacturing, whether it be repair. You can do all that right here, and then operate it from that next room. Now, in addition, once this thing goes on site, wherever it sits, there's also external hose attachments so you can go outside and do work like on a vehicle, for instance. So and then in that case, you would take the heater and the powder feeder out, connect those up, and then do your work on vehicle, and then you're done. So with that, I guess I'm gonna stop there. If there's any questions, feel free to shoot them out. I'll try to answer them. Yeah?
So just with the ocular nozzles, are you able to actually increase stream loading more because you're getting better consistency with the speeds, or do you think it's still limit pace and overall how does it work?
All right. So the question is, with the wide area nozzles, can we increase the stream loading beyond where we would be able to with nozzle 60? So the gas flow through the system is the same because the throat is the same in that nozzle. So I would not anticipate that we could load up the stream anymore. However, I think today we really can't utilize the gas the way we really need to anyways. We can actually load up a nitrogen stream a lot more than we ever do. Typically, even at high RPMs on your powder feeder, you're still only at 2% stream loading for most materials. We can push that up to 5 easily. That's been shown by Sandia years ago. And, and actually Ozone did some work pushing it all the way up to, I think, 40% stream loading. So we have a long way to go on stream loading. We're not limited by the nozzle today. Any other questions? Comments? Yeah?
Is there
Yeah, so the question was, is there an ideal overlap in the step distance when you're spraying and using cold spray? I think it depends. It's a tough question to answer. There's a few things that get into it. One is the waviness of the surface. So if you want the waviness of your surface to be super smooth, then you do have to be careful with what that overlap is. And usually a smaller overlap makes it easier, right? It smooths things out. The problem is, depending on what your robot speed is, you may be limited in, because you want a certain thickness per pass. And that's one thing that I don't know if you saw on that slide with the step. Let me go back here. One thing you'll notice that's very clear is that your bond strength goes up as you go to the larger step. That's because our thickness per pass is going down, right? So we know that thickness per pass being thinner is always better for bonding and for porosity. You can see the porosity got lower too there. So if you are limited in what you can do with your robot speed, then you might have to go to a larger step, which might increase your waviness. So it really all depends on what your goal is. Anything else? Oh, yes. So that's a great question. So the question was, when will the mobile platforms be available for the field, and are we also interested in powder production in the field? So I'm going to take the last one first, because that's a little bit easier to answer. There's already ongoing projects that the Army Research Labs has been working on to do powder production in the field, and there are already systems available to go out to the field and do that work. So I think we've actually tested powder from those systems, stainless steel powders. Those were primarily recovered metal powders. So they were basically taking scrap metal and then shoving it into a melt and producing powders. And that stuff actually works really good. We've sprayed it. It sprays very well. So that system's already kind of available. As far as these particular repair platforms, the trailer-based one is going to be ready in October, and the other one's going to be ready in August, the parts hospital. At that point, they will be tested, and I would think by next year this time, those would be available. Those are OSD Mantech, so those will be used at DoD facilities and so forth, but obviously the technology can be used on the commercial side as well. So that's it. All right, if there's nothing else, not sure who the next speaker is. You okay? Perfect. All right.
All right, so now comes the first fun part of the agenda, where we switch from in-person to virtual presentations. All right, so we've got two coming up back to back. These are pre-recorded presentations. So this is because we've got the international presence, and it's like, I don't know what time in the morning for them. So I'm going to first have the folks from Speed 3D present their work. So it's going to be a virtual presentation here. For the folks who are at home online, you can also post questions, and we'll shout them out to the speakers internally here. So you can use the Q&A box, and we'll take care of those. So with that, I'm going to turn it over to Leah, who's going to turn it over to Speed right here live. Thank you.
Good morning, everyone. My name's Callum Stewart, and I'm a I'm presenting today on behalf of Speed 3D, the Australian manufacturing company, but as you may tell from my tones, I'm not a real Australian. I'm in fact presenting today from Scotland, where I work for Speed 3D in their European program. Speed 3D being a Melbourne-based and a Melbourne and Darwin-based company. Last year, I was in fact an Australian soldier. So I was working with the Australian Army. And the story of the last year for Speed 3D being that I was very fortunate to receive funding, quite a lot of funding, a couple of $1 million or just short of, to run a trial for Australian Army into advanced manufacturing or additive manufacturing. And the Australian Army made a cracking decision in that they were willing to go all in from the very start. And so a large amount of funding to have a proper and serious look into whether distributed advanced manufacturing was of any worth to them. They knew that it was a thing, they knew there was capability out there, but they couldn't tell you truly whether it was of any real worth to them. And the other point of the trial was to demonstrate sovereign capability. So this was another important part. Could the Australian Army do this with Australian technology and Australian people? And in my search for a partner for the project, I was introduced to Byron Kennedy and Stephen Camilleri, who are the founders of Speed 3D. And the last 12 months are, as I say, a history. And we've had an amazing 12 months of bringing the Australian Army light years forward in the latest in cold spray manufacturing. I've got here now a video for you, which I'm going to share, and it will just tell the story of what we've been achieving over the last 12 months.
I'm Lieutenant Colonel Kane Wright, Commanding Officer of the 1st Combat Service Support Battalion. Over the last few months, the Australian Army have been conducting the world's first field trials of a warp speed 3D metal printer. Earlier this year, the Australian Army announced a $1.5 million investment into a 12-month pilot of Speed 3D technology. The program includes the training of soldiers in 3D printing and the trial of Speed 3D's large format warp speed 3D metal printer. The trial is designed to test the feasibility of deploying Speed 3D metal printers, both on base and in the field. Warp speed uses patented cold spray technology that enables significantly faster and more cost-effective metal part production. Developed in Australia, the printer is capable of printing large metal parts up to 40 kilograms at 100 grams per minute. The trial has proven the printer and auxiliary container can be easily transported on the back of HX-77 trucks. This 2-week training exercise at Mount Bundy is the second in a series of exercises in which we are putting the warp speed through rigorous field testing, for example, loading and unloading in various terrains, emergency stops and redeployments, and general operation in austere environments. Soldiers have been training at Charles Darwin University for over 6 months now, learning everything from design to certification of 3D printed parts. They have produced over 50 case studies of parts that can be replaced in the field with metal 3D printing. As an example, here is one of the parts produced today, a bulk fuel module mounting bracket which enables safe operation of manual fuel pumping. This part was designed by one of our trained soldiers and is able to be printed, heat-treated, machined, tested and put to use here in the field. The ability to print repair parts in a deployed environment will significantly reduce our footprint and repair damaged equipment on the spot to get us back to our main priority.
Fantastic. Okay, so that video there gives you a flavour of what the Speed 3D and Australian Army trial was all about. Actually, in the first 6 months, using cold spray, we as an army were able to demonstrate that the technology exists to allow soldiers, and therefore, if you wanted seamen or airmen, military members, to take the latest manufacturing techniques out into the field and use it to make real worthwhile parts. And this is what defense forces around the world are looking for. And specifically, defense forces, having been there and been in that environment, we need a capability that is deployable. Now, the topic for this part of the conference is cold spray at the point of need. And I was asking myself, what is the point of need in Army? Where specifically is it? Now, there is no one location. Armies will always say they want to repair and maintain equipment as far forward as possible, to keep that piece of equipment in the hand of the user so the fight can go forward. The true is at sea, the same is true at sea as it is in the Air Force. And so some photos here to demonstrate the different environments in which we took our cold spray technology. So if you look at the top left, that's either day 1 or day 2 of the Australian Army having a cold spray technology in its workshop. And that is big industrial warehouse, lots of tradesmen from draftsmen, fitters, turners, electricians, vehicle mechanics, all working under that sort of environment on a day-to-day basis in their barracks. And if you are in Army, you would call this second line support. Okay, it's within the brigade environment. You wouldn't take this sort of technology any farther forward than this point because frankly, it's too big, bulky and not maneuverable. This is absolutely the limit of where you can take a manufacturing capability. And it's actually very testing to get it that far forward. Because whilst the top left there shows you a warehouse, second line support exists in the field as well. If you look at your photo on the right-hand side, you'll see this was within 2 weeks of having the printer in Darwin with my battalion, we took it out into the field. There you can see me with the big green arrow. That is obviously a Ferrari red or a Speed 3D red industrial printer. And we have pushed ourselves from the very start to see if it can survive the rigors of the field. And this exercise was specifically about, can the technology survive the simple things of field life? That being, can you pick it up, put it down, and we're talking on the back of trucks, set it up, get it running, calibrate it, repair it if needed, and use it. How noisy is it? How much light does it emit? How tactical can this sort of equipment be? Now, obviously, this is the version 1, taking it into the field, but valuable lessons. But that's a fairly benign environment, looking at it. Bottom left was the second exercise that we took the cold spray technology on. If you look at that bottom left picture there, which is a great picture, you'll see the printer in the middle of a dust storm. On the far left of the photo, you'll see the generator and the dust extractor, again, easily moved on the back of the Australian Army's Rheinmetall trucks. And on the right-hand side, behind all the ponchos, is where the rest of the manufacturing unit was housed. So we're talking the soldiers with their CNC machines, with their test equipment, with their heat treatment, and with their computers so they can do drawings. So the point of need for Army, this is as far forward as you would get it. In modern day environment, what would that look like? We're talking Afghanistan, we're talking Camp Leatherneck, we're talking Camp Bastion. It would look something more akin to what you've got in the top left there, but in the theatre where the soldier needs the part. There is no point in Army's view or in the mind of Army Defence of having this sort of capability and having it in a different theatre or a different country from where the soldiers are. where the customer is. So if I was to move on now and demonstrate a couple of the parts that we've made in this chow using cold spray. Here we have one of the relatively new Australian Army fuel trucks, bulk fuel capability. It's a Rheinmetall stroke MAN truck and an Australian fuel system on the rear. There are maybe half a dozen of these that would support one brigade, one fighting brigade, so let's say a few thousand soldiers. And they are battle-winning bits of equipment because without fuel, your army doesn't move. So if these break, these are the #1 priority for repair. And this is a brand new bit of kit. Now, with every bit of brand new kit, there are always points of failure, and that's to be expected. So there's no finger pointing here. But one of the parts on this vehicle that we knew consistently failed was this, a mounting bracket. Simple mounting bracket, nothing difficult to it. But that part allowed you to prime the pump, and it was shearing. It's actually made of 2 parts. It's a swivel. You can only see one part at the moment on the slide. But they don't exist in the supply chain. Now, if this was Afghanistan, do you say we need to fly this part from around the world into Afghanistan? Or worse still, do you go to your supplier and find out that it isn't in the supply chain and that you need to wait for the part, then to fly it out? Or do you say we have our own manufacturing capability, but it's in America or it's in the UK or it's in Australia, it's not in the theatre where we need it, and say to that manufacturing organization out of theatre, we need you to make a bulk fuel module bracket for us. Okay, where's it breaking? What's going on with it? Well, the customer's in Afghanistan. That's a pretty difficult conversation you're now having to have with a customer in Afghanistan, a design team in another country trying to make a bespoke solution for you. This is why defense forces understand that distributed manufacturing at the point of need is in theatre. It's not straight as far forward with the fighting troops. That's one step too far, but it is absolutely in theatre where the customer can engage with the manufacturing facility. So cold spray at the point of need. What does that look like for defense forces? It's certainly in theatre, and it's as far forward as you can get it, where the customer can meet the manufacturing facility. Now, just, it's nice to see there's a real metal part of real worth to the army, printed in 30 minutes. The soldiers that designed it, it took them a couple of days. This was one of their first parts. It took them a couple of days to come up with the drawing and design it and have confidence in their design. The print part was particularly easy. The testing part, Speed 3D, held the soldier's hand through that process to get them through a proper testing process. And at the end of it, you're asking the commander of that defense force, are you happy with this part being added to one of your vehicles? When the original part, when the real part is available from the supplier, we'll use that part. But until then, this is the manufactured solution. And it's a classic example of what's the cost of not having this part versus what's the cost of the part. We get asked continually, well, is it not cheaper just to go source it and fly it in? Yeah, but when do you need that part? And what's the cost of not having it in time? But these are all arguments which in our industry, we all understand. There's a part actually being fitted to the subcomponent of the vehicle. Next part, I'm going to move quickly because I realize we've only got 30 minutes for the whole segment, and Vic probably wants to chat. Gunner's ratchet, 300 armored vehicles, M113s, buckets in Australia. 5 out of every 6 do not have this piece of crew equipment, simple gunner's ratchet. It's a very old vehicle, it's an old gun, and therefore it's no surprise that the tooling that goes with it over time breaks, disappears, gets lost. But they're crucial. You can't maintain the gun without this spanner. 6 months to get it made. We've had quotes in the army of up to $1,000 Australian for this part. Speed 3D had it as one of the case studies within the trial, And you can see the results there for yourself, just how quickly and how easily it was for us to provide capability using our technology. And again, where do you do it? You make sure you're doing it in theatre as far forward as is practicably possible. Final piece, the Australian Army have a particularly old fleet of landing craft. So we're talking beach landing crafts vessels. And no surprise that when it comes to pump housings, particularly I think if the original is made of aluminium, it's going to corrode, it's going to fail, it's going to break. And we are talking Vietnam era technology or Vietnam era vessels. And these fail regularly. And it was one of the more complicated pieces that the soldiers had to redesign and print. But again, where would you be doing it? You would be doing it in theatre as far forward as possible. So what's next for cold spray as we see it here in Speed 3D? We are having fantastic success with the Australian Army. We're going gangbusters. And we are in discussions with other defence forces around the world and defence primes. And the conversation is always about use cases. Am I going to be able to make use of this capability, of this technology? This example here, Titan, is the British Army bridge layer. Tanks can't go anywhere if they cannot cross large gaps. Tanks are useless at crossing large gaps, so you need a bridge. And it's, as you can see there, Titan carries a bridge on its shoulders and drops it over the gap. Titan came into service in 2006 and it has 1,400 components that are no longer available in the supply chain. This is where cold spray gets into its defense market. I've went back and I've watched some of the presentations from the previous workshops, in particular, Dr. Champagne's presentations at the start of each year. I see his timeline of what's happening with cold spray and what he expected to happen over 10, 15 years. And the final stage being near net parts. We are absolutely at this point with cold spray. So long as you can deploy it, so long as you can get it into the theatre of use, you have a market for cold spray because the parts that are being made are to the standard required. And that standard I always coin in defense is good enough. The standard is it good enough for the job? I'm going to wrap up quickly because that's me been going on for 18 minutes. Point of need, as far forward as possible in the theatre so the customer can engage with the manufacturing facility. Your technology needs to be soldier proof. It's soldiers, seamen and airmen that are going to be using it. And therefore it's got to be modern, it's got to be engaging, and it's got to be robust. When engaging with defence forces, provide a bluff bottom line up front. This is rapid manufacturing. It is not 3D printing. Down the bottom there, this is something, as the customer in Army, I got frustrated with immediately. Is this 3D printing or is it not? 3D printing, in my mind, I thought it was Star Trek stuff, replicator stuff. We all know that's not the case. It's rapid manufacturing. It's part of a process that defence forces want to be able to provide sovereign capability to manufacture. This is a great addition, but it is not a Star Trek replicator. Tell your customers this in advance. And the second to last one there, the quality standard for defence will always be good enough. It does not need to be to that of the original. It needs to be good enough for them to use it in the mission over a period of time that is defined by the commanding officer or commander who holds the risk. The supply chain will always hold primacy. Cold spray finds its niche in supporting and adding rigor to that supply chain. So if you have a 6-week gap for a bulk fuel module mounting bracket, and you can provide one for those 6 weeks, and it's only going out in 3 missions, and the risk is low, that is good enough. And that is the standard that cold spray needs to aspire to. That's me bang on 20 minutes. Thank you, Cold Spray Action Team, for the opportunity to speak. Hopefully after this, you'll see me online and we can have some discussion and some questions. Yeah, thank you very much. It was a pleasure to be here.
All right, so we should have Callum on here in the background, maybe. We'll know in a second if we can hear him. All right, fabulous. So we have a couple of online questions, and we'll take questions out here as well. So the first question coming in is really around the kind of part performance, right? So you talked about quality being kind of good enough, but you know, when you get in those situations where maybe you need more than just good enough, what kind of performance are you able to get out of the properties that the materials that you're putting down? Are you able to achieve anything structural, and kind of where does that fall into the timeline of kind of speed's printing capabilities, if you will? Very much. So I have more questions online, but I also want to open it up to the audience here as well. Do we have other questions from the audience for Callum? We have a few minutes here. Okay, we'll keep the online questions going then. So another question, cost of the warp speed system, and really when you talk about, you know, training of the soldiers on the warp speed, can you describe in more detail, you know, what is that training like, and how kind of scalable is that training program as you try to deploy more of these out in the field?
You need to take them through. And so the Australian Army
Thank you. So I think we have time for maybe one more question here, and we've got a bunch online, so I'm just going to take that one since nobody here is raising their hands. But the next question is really about materials and property performance. So are you able to highlight just kind of a few of the materials and the associated performance that you're able to get out of them? You mentioned cast properties, but if you could give some more color to that, I think that would be beneficial to the community. Understood. Awesome. So we are at time. Thank you so much for being part of the CSAT hybrid event here. This has been fantastic. For those of you who are here in the room, Speed has a booth out in the back. You can get all the rest of your questions. For everybody online, remember, there is actually a virtual presence to all of the exhibitors. So whether it's Speed or VRC or any of the other presenters today or exhibitors, you can see them in person here, but you can also see them online. You can go to the Cold Spray Team website, you can click on the Zoom links, and you can actually interact with folks who are at their virtual booths, both, again, here and online. So Callum, thank you so much for being here. We're going to jump over to our next speaker, and I was actually wrong. Neil Matthews, a stalwart supporter of the Cold Spray Action Team here for a very, very long time, is live with us in Australia. So he's going to be popping on here in just a minute. So I'm going to get myself off the stage, and Leah, if you can kick us over to Neil Matthews, we'll let him present for all the work that he's doing over with RUAG.
We can hear you. Yes, Neil, we can hear you in the room. Thank you. You can continue.
we decided, we looked around and we selected an Australian bird called a brolga. And the reason we did that is if you actually look at the mobile system in its operation, it's obviously got an extendable arm. The brolga is a bird that has a long, slender neck and stilt-like legs. It moves to different areas in response to conditions. They have social units of fairly small, in about family groups of 3 to 4, and its initial startup is a bit ungainly. But once it gathers speed, it's graceful. So we thought that filled a good definition and a good use of a short word to describe the system. So that resulted in that first system that Vic showed, which was the one that was basically trialled on a number of US Navy bases, and that was sponsored by NavAir through VRC. And we have established an agreement and a relationship to basically take our knowledge of configuration and integration into mobile systems going forward. We're currently working on the Brolga 2, and we look forward to further iterations of the mobilisation, and could be on different platforms in different configurations, but the concept of taking that technology to the target is our focus. Next slide, please. So as I say, we started out with a field portable SPD unit, 001. We demonstrated that to our Navy in 2010. We've taken it to Air Force bases, and that was an extended application to demonstrate application on a P3. We've taken it to Edinburgh, so these bases are fairly well dispersed around Australia, and we then took it to our Defence Scientific Group for an application on the centre barrel, which underwent full-scale fatigue testing. So this was really where we actually saw the ability to take the mobile technology and apply it in structural applications and structural areas. Next slide, please. So from there, we've developed a number of systems. This system here goes from that original system to what we call Brolga 0. It's the one that we have in our facility. We've replaced the old CGT gun and the powder feeder. We've generated power distribution boards, gas supply, interfaces. So we've got the HMI screen interfaced into the system, and we got rid of the gas cage, because we felt that most of the applications that we were using had access to nitrogen and external power. And we've modified a number of those elements as we evolved the design. So that's the unit that we have and we currently use in our facility, and certainly the one that we will take on the road for demonstrations as we go forward. The next slide, please. So this is basically now its current configuration. That's our current configuration. As you can see, we've basically generated a main supply unit, full of the gas train and some of the other elements, a lot of the module and the PLCs, and predominantly made of commercial off-the-shelf components. We've repackaged the circuit boards and made them dust-proof for field operations. So we're continuously aware of the customer requirements and also the supportability through the utilisation of commercial products. Next slide, please. The recent applications, what we've done there is, whilst I love robotics dearly, there are applications where we have seen where it's just more practical to basically use the handheld. So what you see there is a fairly large repair we're currently doing, and it's a Chinook sump cover, heavily corroded in all areas, particularly around Roseanne fittings, so we've had to replace and pull out existing fittings and really look at the SPD in some of the fastener holes and around the fastener holes. A lot of the time in this is programming the robot. It's more difficult with holes, we've found, because they're not in where I call predictable positions. They're not necessarily where the drawings say they should be. And for those applications, we've felt that the handheld enables us to do that. We've just done some work for another customer on producing a whole range of test samples, and we had the opportunity to do the particle measurement, which again shows us that we're getting very, very good distributions and velocities where we need them to be above 700 metres a second. And these are depositions of 2000 and 7000 series aluminium. We also used the opportunity to continue to look at the impact of thermal issues, thermal stresses, and the potential of those. These are particularly of interest when we look at the durability and the fatigue behaviour of some of the applications, particularly in highly loaded and highly stressed areas. Next slide, please. So the Brolga one, which is the one that that effectively went to the States, it's a NavAir unit, and I'm sure Fred will touch on that a little bit later. But it's been to a number of bases for test, and the reports back were very encouraging, and we would hope that we'll see more of those units in the near future go into areas of bases. Again, the biggest difference with that one to ours is that's got a gas cage still on it, and it's got basically a remote HMI panel, which we've decided we can better incorporate it into the power unit. Next slide, please. Okay, and that's a brief rundown, and I'm sure if you want any information, either VRC or Fred can take you through those. We effectively sent one of our guys over to do the validation and verification. Going forward, and with our relationship to VRC, we'll probably do the assembly in the US. It makes a lot more sense. We can tell you that it's easier to buy a trailer in the US than to air freight one, even though ours are probably damn fine. But there are some logistics that we can do. And what we are doing is that the current designs are extremely modular and can be repackaged, unpackaged for customer applications. So obviously what we're always keen to do is to give that accessibility to the target, and where possible use that robotics again for the reliability and the repeatability. And I believe that that unit that we have supplied to NavAir is being used in situ for some helicopter repairs. I think it's the skids, but again, Fred and perhaps other people who are closer to the unit can give you some more information. The next slide. So, and again, Aaron's already introduced this one, but this one's, I call, a bit of a monster. There is some elements of Brolga 1 into it, very remotely. The fact that it fits on a trailer, and there are module elements, and there are gas bottles, and that's probably about where it starts and finishes, I think. The initial concept was to have the power generation on this one skid, if you like. It very quickly came to realise that you couldn't put all of these on a system to have on a trailer-based outcome. So the power generation now is, the generator sits off on another vehicle. So what we've done is we've put it on a trailer-based system. All the development, the module development and things like that we've done in Australia. We will package that up. This will go over as a complete system, with the exception of the VRC components. Any future programs will obviously go across as a module rather than the whole trailer assembly. The next slide, please. So when I say it's a monster, if you look at the highlights in yellow are the small changes from the existing smaller package Brolgas, which are very versatile and work extremely well on bases that are serviced with nitrogen and with power. This thing comes in at about 4,000 kg, and it's a 15-foot trailer, so it's quite a large item, but it has everything on board that one requires, and that was the requirements of the customer. And I think all it shows is that this technology can be modulated and can be compartmentized and can be delivered in various forms, as we've seen. We've retained the robot again for those critical elements of structural application. Next slide, please. And this is just an overview. So we do have the trailer. It's in our shop now and it's being fitted out. So it's well on the way to getting it across to the good US of A as soon as we possibly can. I think a lot of design activity has gone into the deployable cold spray platform. It looks like it's an outer space. If we go to the next slide, please. So you'll see all the various modules. Again, they can be rearranged, repackaged for whatever the customer wants, but I think the iterative nature of the design between ourselves and VRCs has led us to what we think is an optimum solution, and we're obviously down the track of now manufacturing that particular concept. Next slide, please. And this is very interesting because you've now got a mobilised trailer. You can basically, again, take the technology closer to the target without having all the trailer elements in there. This has been an evolving and interesting design program. Looks like it's space age, but that's all weight reduction. And I think I spoke to the guys who are actually doing the assembly now, and there's probably over 100 bits and pieces that go into that structure. But it's obviously designed for stability. We're very conscious of the heater and where things sit. It's all accessible, so lots of bells and whistles in this little package. Next slide, please. And where we go in the future, what we believe is, and we've picked up for the future systems that we've quoted for, what we're effectively doing is we're picking up many of the features that we've put into our Brolga Zero. We think they're significant improvements. A lot of those improvements came out to the validation trials of the initial Brolga. So we've picked on those. We've added a few more in to basically meet customers' requirements. So quite a slick little unit. It is a high pressure system, and as I say, it's obviously the robotics are quite a significant part of that. Next slide, please. So I just want to touch on very briefly, I'm watching the time, so we continue to repair aircraft components. The latest one we've done is a sump cover. The amount of corrosion and the amount of requirements for application are quite significant, and it's required a fair amount of activity in both the modelling, the machining and those sorts of elements, but the outcome will be that we'll probably put back into service something that will have a much, much longer life. We're incorporating the new coating technologies of Tagnite as well, so that's progressing extremely well, and we continue to repair F-18 components, not only for ourselves but for our mothership in Switzerland. And there's a lot of interest. We are starting to get US Navy wheels as part of an agreement, and we're starting to implement those repairs as well. So that continues on, and there's plenty of other opportunities and other platforms. Next slide, please. This is one I just want to touch on briefly. So we've had the opportunity to actually implement cold spray, tungsten carbide as a replacement for chrome plating on a new aircraft. This aircraft that we have here is called the Loyal Wingman. It's designed in Australia, built for Australian operations. It's the first aircraft we built in Australia for about 50 years. Designed and built. It's obviously done and built in collaboration with Boeing. Just to give you a feel for this little device here, it's about 38 foot long, 24 foot wingspan, and 2,000 miles of capacity. What you're seeing is on the lower right-hand picture is a landing, so it has test flown, it has landed. That has a number of tungsten carbide applications on both the main and the nose landing gear. We are manufacturing that particular item. So, and Boeing has accepted that as an approved coating technology. So we think that that gives us a lot of strength going forward on that particular aeroplane. Quickly flash through the next slide, please. If you can go to the next slide. Thank you. And that's just some indications. So we're coating very small bits, but again, quite large pistons and things like that. It's a single coat deposition. The challenge was, interestingly, after you coat it, how do you machine it? So that's produced a challenge to our machinists. But we've got there, it's a very, very highly polished finish, and it performs extremely well. The last slide, please. So we've done an enormous amount of work with Monash University on durability over the last 12 months. We see that the overarching requirement for this as a structural application will be to adhere to the durability requirements that are detailed in that USAF Structures Bulletin. We believe that if we can meet those and be able to analytically evaluate SPD cold spray repairs, then we will have achieved a significant amount of evidence to go into acceptance. Reece, Dr. Reece Jones, an eminent man in this field, is going to talk in session 4, and he'll present the results of the work we've done to date. What you see there is the analytical modelling and the actual test results. So you can see they align extremely well. In fact, people have said, so what have you done? Just drawn a couple of lines on dots and called them analysis and experiment. They are real results both that way. So the predictability, both of the repair of the SPD behaviour and the substrate behaviour, are very, very good, and we can take this forward when we present the opportunity for structural applications. And at that point, I'll call it quits. So thank you.
Thank you, Neil. Wish we could have seen your good-looking face here in person, but as usual, great talk, wealth of information, hitting all the high points that I wanted. I'm going to take us into break, but beforehand, do we have questions for Neil? I'll ask the in-house crowd first. With all these systems, okay, sure, Gene.
How does the cold spray carbide landing gear, including compared to the HVOF, carbide cobalt, which is also
Yeah, so Neil, so the question is on that landing gear, how does the cold spray wear coating, you know, the tungsten carbide cobalt, compare to the HVOF?
In terms of micro cracking and all sorts of things. So all the indications, the wear results that we did in comparison with the two, it's much, much better wear characteristics. It's got a much, much better finish. So we think it's and the bond strength is much greater than the coatings. And the other thing is, obviously, the biggest issue, it eliminates any issues of thermal activity that you would have with HVOF. So we didn't have to go down that qualification route of trying to demonstrate that there was no ill effects on the substrate.
Right. Yeah, and I can add a few things too. And actually, it was Aaron Nardi who first, brought this to light several years ago when we were first developing that material. He took a hammer to it. All right, remember you told me, I said, that'd be great, you know, like I love theatrics up here, and you know, maybe that's what we'll do next go around is have you know, have an HVOF version, have a cold spray version, take a hammer to it and see see who wins. But it does dent, but it doesn't fall off and crack, which I have heard has happened over the last few years. So yeah. Any other questions from the internal crowd? Yeah, Tom. Right. So Neil, the question is, and again, in regards to these high hard coatings, machining of them. Is there anything you can share in terms of the you know, the tools or the passes or the you know, working pressures, anything?
All I know is that when we gave it to our machinists, they said, "You've got to be joking. You know, how in the hell do you expect us to machine this to your surface finish?" It took a lot of iterations to get there. Obviously, the cutting wheel is the material on the cutting wheel is critical. The other thing we found out very, very quickly is, even though machinists like to take big cuts, the best way of treating this stuff is to take small cuts. But the deposition is fairly even, so we don't need to be aggressive with the machining. So if you take the machining in small bits, you'll get there very, very quickly if you try and remove it. Now, we're putting coatings down probably of the order of 7 to 10 thou. So these are a single coat deposition, and we're getting very, very good density, no porosity, and we're just machining it. So we basically have defined the thickness to minimise the amount of material removal during the machining process.
I would imagine are all diamond tip. I mean, even the conventional HVOF, I mean, that's how you would do it. I don't think there would be any difference. I mean, it's the same darn material, approximately the same hardnesses, so I would not imagine it would differ from machining of the HVOF. Any other in-house questions before we go to the online? Aaron, any?
Yes, we've got a couple online. First one, just for the hard coatings, what is the hardness that's being achieved and how is it being finished? It sounds like the machine, but they're also curious if it was ground, like you would have to with some hard coatings.
Yeah, I mean, so Neil, the two-part question. What are the hardness ranges of the tungsten carbide, cobalt? And also, again, they're asking about machining. Is it's more of it's a grinding operation. I mean, it's not, you know, use the word cutting, but I would use the word grinding. But it's a two-part question. So hardness and technique for finishing.
I don't have those hardness details with me, and I can give you some indication on what challenges we had and what the strategy was for machining.
Next question is around the temperatures and pressures that can be achieved with the mobile system.
Yeah, so with the mobile system, Neil, what are the pressures and the temperatures that can be achieved?
Okay, well, so, and I can refer that to Aaron. So we're basically, all the parameters that we get out of the VRC system is delivered by that. So I think that's 1,000 PSI, 800 degrees. And again, what we're looking at the moment, predominantly for the high-strength aluminiums, that's where we're focused at the moment because that's where the customer need is. So, and as I say, I think I demonstrated that we have measurements. We're in the 700 metres a second mark above that, and that gives us the deposition characteristics we need.
Yeah, so the answer is, 1,000 PSI at about 800 degrees C gun temp. Any other? All right, very good. So if there's no other questions, what we'll do is have a break. And what time are we supposed to be back here? What's the agenda say there? 10:30.
10:30.
All right, very good.